Okay, so just a quick recap again because I wasn't recording just yet. The homework you picked up today will be due on Monday. The focus activities, you'll get the second one tomorrow, third one on Monday. They are officially due Wednesday of next week. The homework, I said is Monday. What's coming up Thursday? The test. So a week from today is your first exam. It's going to have domain range, all this information on there, piecewise functions, sets, so intersection, union. In fact, the quiz, your homework, that's pretty good idea of what to expect. Okay, well, let's go ahead and get to it. The sooner we get through, the more time you have. On average, I would say all the classes have been having about 15 minutes so far for the quiz, which I think is more than enough time. Okay, but we'll see. All right, so we ended here yesterday. We talked about this rational function. This one right here, the way the problem was given to me, was that implicit or explicit? What do you guys think? Rhett, what do you think? Implicit, yes. If we solve it for the dependent variable, y, then it becomes explicit. Yes, okay. And that's what we did. And what was the one thing I asked you to take a look at last night? The domain and the range. So hopefully this is what you're going to have on your paper. If not, let me know. So here, because of the vertical asymptote, I can say negative infinity to 0, union 0 to infinity. Okay. Now that is equivalent if you go ahead and say all reals, you would just have to tack on except x cannot equal 0. Because remember, 0 makes the function undefined. How do we do on that? Okay, good. So some yes, some no. Here's the range. Now you can definitely tell the branches, there's going to be a vertical overlap. So again, this one, the range is simply going to be all reals as well. Okay. In fact, does anybody remember what we called that slant asymptote? Kimberly? Started with an O. No? Saul? No? Varunda? Oblique, yes, very good. Oblique. All right, so I'm going to go ahead and take that off for the next class. All right, let's go ahead and continue. Now, one of the things that we also brought up yesterday, but we hadn't had a chance to discuss yet, was the idea of increasing and decreasing functions. Now, remember, this is where the y values are going to be getting larger, smaller, or remaining the same. This is driven by the y values, but we use the x-axis to go ahead and describe where that happens. We use intervals on the x-axis. So let's take a look at this first one. A says this graph falls, so that means we're looking for a decreasing section. So think about it, bless you. You're always going from left to right, okay? X is always going to be increasing, whether you're looking at increasing, decreasing, or constant for the y's. As you go from left to right, are there any sections where the y values get smaller? Okay. And maybe for this first one, I need to go ahead and kind of point you in the right direction. Let's take a look at this guy right here. Let me use a red. Look at this point right here. See, as the values of x continue to grow, what are these y values doing? They're decreasing, so they're getting smaller. So it's almost like you're looking for regions where you're going to have a positive, negative, or a zero slope. Okay? So now, to describe where this happens, you use the x-axis. What's the value of x where it begins to decrease? -1, and where does it stop? It stops at 1. So on that interval, we can say this function is decreasing. So I'm going to say -1 to 1. Okay. B says the graph is constant from what to what?
1 to 5.
There we go. So from 1 to 5, any value of x that I put in right here, it's always given me the same y value. It remains constant. So from 1 to 5. Very good. Okay. So increasing, decreasing, is this making a lot more sense?
Yeah.
Okay. So is there any place where it's increasing? There you go. From 5 to 7. Okay, now let me go ahead and erase what I've done to the graph real fast. Now, we've identified where the interval begins and where it ends, okay? So let's say I did want to go ahead and write the interval in interval notation where he increases, where he rises. Well, I'm just going to go ahead and say 5, 7. There's going to be something you're going to be very tempted to do. So what am I referring to? What did I not do when I wrote that interval? The brackets, that's right. You'll notice we do have a closed circle there. We got a closed circle there. But when we're talking about increasing, decreasing, and constant, we're not concerned with inclusion. I simply want to know what intervals, where are the y's getting larger, where are they getting smaller, where are they staying the same. Okay. Now, if you do go ahead and put the brackets on there, it's not a big deal, but just so you know, we don't have to do that in this concept. All right. So let's go ahead and try one. Use a graphing utility to determine the open intervals on which the function is increasing, decreasing, or constant. So if we had more time, I would absolutely love to, break this graph down, find the roots, go ahead and talk about the end behavior. But for right now, we'll just go ahead and use the calculator. So I have a cubic function, x cubed minus 3x squared plus 2. All right, so let's see here. Let me go ahead and document B out here. So I'm going to go ahead and say x cubed. What was it? Minus what? Minus 3x squared plus 2. There we go. So minus 3x squared plus 2. Okay, so I'm going to go ahead and graph this. So we see this guy right here. Now, depending on your graph, maybe it strictly increases. Maybe the y's increase without bound and they never stop. Maybe the function will always decrease. Maybe it could do both. Okay, what's happening here? It is doing both. Can anybody tell me an interval where along the x-axis it's increasing? Okay, now I heard 0, so we're going to start right here on the y-axis. To what? To 2? Okay. So we're talking about here and here, right? Now, I just went ahead and drew a line on the left just to kind of show you, get you to start looking at this interval, okay? Where does y stop increasing for the left part of the graph? Stops at 0, because as x increases here, you'll see the y values start to decrease. So we're looking for increasing, right? So we know an interval is that it stops at 0, but where does it begin? Or does it have a beginning? Because here's my question. This part of the graph, the left end behavior, is almost vertical, okay? But how far down is he going to go? He's going to go to negative infinity. And see, here's the thing. The key word I said there was he's almost vertical. He does have just a slight slant to him. So how far out will he go? He'll go out to negative infinity. Now, it's going to take him a long time to get there, but he's going to eventually be able to push out all the way along the negative x-axis. Okay, so one interval where this guy's increasing, I can go ahead and say it's from negative infinity to 0. Remember, you're looking for where the y's get larger, get smaller, but you list them using the x-axis. Okay? All right, so it doesn't matter what the y's are or what they're doing, it's the x's that tell me where it's happening. So let's try another one. Okay, what other location is this guy increasing? There you go. Because right here, when x is 2, you can see there we have a turning point, right? This is where the y values are going to start to go up. And you're right, he goes forever without bound. So the other one is going to be union 2 to infinity. So this one had 2 intervals where the y's are getting larger as x gets larger. Okay, is there an interval where we decrease? Yes, from what to what? There you go, from 0 to 2, right there in the middle, anything I plug in as x gets larger, the y's are getting smaller. Okay, so that's between 0 and 2. And is there any place where y remains constant? No, this one does not have anything like that. So for this, I'd probably just say like none. Okay. Is that making sense? Let me go ahead and take this off real quick.
Would it not be of 0 to like 1.5? It's only increasing at that.
0 to 1.5. Well, because the turning point is right here. See, that's where we stop going down and we start going up.
Yeah, so that would be the part where it decreases to that like point.
And see, but that's why we don't include that point when we're talking about these intervals. Okay, because it's not changing sign at that point, but that's where the boundary is. I don't know if that kind of helps.
Yeah.
Okay, let's try another one. Okay, so let me document B out of here. And the other one is, what was it? The absolute value of x plus 2 plus the absolute value of x minus 1 minus 2. Okay, so you'll notice on your screen, and let me use the keyboard and the mouse since I'm recording this, but you may already have a place on the Inspire where you like to find absolute value. You may already be comfortable with it. I like to use this button right here. It's halfway between the 9 and your catalog, the open book. If you push it, you're going to get a ton of options. You have ratio, exponential, you've got radicals, the natural number, okay, piecewise functions, you can differentiate. Okay, that's going to be very useful to those of you going into calculus. What are these? Matrices, okay, and you have integrals, but that's, you don't need to know about those right now. But right here, that's already highlighted, that's absolute value. Okay, so I'm going to go ahead and click it. Well, I might want to be on my graph. Okay, so, and what was the function? Plus 2 minus 1. Okay, so this was x plus 2. And was it plus or minus? Plus. And then I'm going to bring up the absolute value again. Where this was, I believe, x minus 1. And then it was a minus 2, correct? Okay. So here we go. So we have a graph very similar to the one we started with. All right. Now remember, I'm interested in taking intervals off of the x-axis that tell me where the y's are increasing, they're decreasing, or they're the same. Okay, so take about 30 seconds. Okay, 30 seconds, write down the intervals, if any, where they do this. And then we'll go ahead and quickly check our answers in just a second. Okay. Mm-hmm.
It just gives me a syntax error.
Really? That's interesting. I don't know. Let's try Control W. Let's try this. What is it? X plus 2, and then plus
X minus 1.
X minus 1 minus 2. I don't know. You were in a document. I don't think that would have anything to do with it, but there you go. Okay, technology. All right, so that's been 30 seconds. So let's start with increasing. Is there any place here where the y values just get larger? Where? Okay, it only happens from 1 to infinity because this guy's going to go forever. Okay, so from 1 to infinity. Is there any place where he's going to decrease? Negative infinity to negative 2, yes. And did this guy have any place where the y's remain constant? Okay, where you had a horizontal segment. Negative 2 to 1. That's exactly right. Okay. Perfect, perfect, perfect. Good. Okay, questions? No? Okay. Well, let's go ahead and take a look at relative maxes and mins. Okay. So we have some more definitions here that, again, are probably about as clear as mud, but I'll see if I can help you sort through it. It says, for any function f, if there exists an interval. Okay, so someplace on your graph, you know, where you have maybe x sub 1, x sub 2, just like we were talking about. You have an interval from one x to the other that contains some value c, so that for all x not equal to c, so c has to be between the two. It can't be one of the interval boundaries. Okay, in the interval 1, then f has a local maximum at c when f of c is greater than f of x. Okay, a local maximum when it's greater than the function itself. Okay, now if f has a f of c less than f of x, we refer to that as a local minimum. Okay, so let me see if I can explain this and try to help you out. Now, unfortunately, this graph doesn't show it, but we have to believe that we would have arrows at the end of that, okay, to indicate that this guy's just going to continue to go forever, right? So if I were looking at his domain, okay, because of the slant on the end behavior, he's infinitely wide and he's definitely infinitely tall. Okay, well, let's say that you do have a graph, maybe like a parabola. Okay, now the maximum and the minimum refers to your y value. Okay, it refers to an element in the range. Now, this graph right here has what we call an absolute minimum, because there is no y value on the graph smaller than the value of that vertex. Okay, just the same, if you say had a parabola that opens up, this would be what we refer to as an absolute maximum. It is the largest value in the range that you're going to find. Well, that's not what we're dealing with here. We're dealing with what we call relative maximums and relative minimums. So look at this graph. Okay, take a look in particular at this point right here. Okay, now because this guy is just going to continue to go forever to positive infinity, would that point in red be an absolute maximum? No, because obviously there are y values that are going to be larger than it, right? But what we're saying is, if we go ahead and look at the function just on a given interval between two values of x that we choose, then on that interval, he can be a maximum. Okay? Because he's not the largest, we refer to him as the relative maximum. All right? And the same thing applies for the valleys. I kind of think of these as mountaintops and the valleys. If I take an interval here, okay, he's definitely not going to be the smallest, but on that interval, he is the smallest. So we call him the relative minimum. Does that make sense? Okay. So I've already labeled two of them for you. So this right here would be the relative max, or a relative max, I should say. This one right here would be a relative min. What's this other one right here? Would he be a relative max or a relative min? He'd be a relative max. What about this guy right here? He's a relative min. There you go. So it is possible to have what we call an absolute maximum or minimum, but that is the largest y value the function will have. So if it does go forever to positive and negative infinity, these little mountaintops and valleys, they become what we call relative maximums and relative minimums. Okay. So let's try finding some. Now, we already have this sketched, so I'm going to go ahead and put it in the calculator in just a second. This is x cubed minus 4x plus 1. It says we want to determine the local extrema. Give values rounded to 2 decimal places. Okay, so we're going to go ahead and do this by technology, and then I'm going to very, very quickly show you how we would do this using calculus. Okay, so if I lose you on the calculus portion, that is okay. This is just kind of like a foreshadowing of what's to come. All right, so hey. Oh, yes, yes, please, please. Because this is the larger class, yes. If you're 31 or above seat number, yes, I have those on the desk. Okay. All right. I'll take care of the roll later. So let me go ahead and plug this in the calculator. Let's do this by technology, and you might already have an idea how to do this. X cubed minus 4x plus 1. So, So let me document B out of here. Okay, so x to the power of 3, what was it, minus 4x plus 1? Okay. So there's the actual graph that we have on our paper. Okay. Now, what I'm interested in is first finding this guy right here. Okay. Now, how would I classify him? Is he a relative maximum or a relative minimum? He's a relative maximum. Because if I put an interval around him, he's definitely not the largest, but he is a mountaintop. Okay, he represents a turning point where the y values say stop increasing and they start decreasing. So think about this point itself. The y value is the relative max that we're looking for. Okay. Now, when the paper says occurs at, that's the x value. We want to know what value of x that it occurs at. So that's what we're going to go ahead and find very quickly. All right. So does anybody know how we do that? Using the calculator? Menu. Okay, so we're going to hit menu. Then what? 6. Analyze graph, and you'll notice we've got minimum and maximum. So I'm going to choose maximum. Now, it's going to give you a vertical line, and it's going to say lower bound. So when it says lower bound, that means we want the left side. So we want to move that vertical line to the left of the point I'm trying to find. We're trying to find this guy right here. So I'm going to move it just to the left, and then I'm going to go ahead and click enter on my calculator, or you can click your touchpad, but it's going to mark that location. And you'll notice it says what now? Upper bound. As soon as I slide my vertical line to the right, it creates a shadow region. As soon as I get that point, it'll automatically pop up and tell me what it is. Okay. So I know that that relative maximum is 4.08, and where does it occur? Yeah, so this x value right here, it's really close to -1, -1.15. So 4.08 and -1.15. Okay, and then I want to go ahead and do the same thing to this guy right here. How would I classify him? He's a relative minimum. So again, think about that coordinate. That point right there, the y value would be the relative minimum. And then we want the x value where it occurs. Okay, so if I go straight up from here, more than likely I'm looking for a decimal between 1 and 2, right? Okay, the technology is going to give me that exact. So let's see. Let me come back over here. I'm going to go to, you said menu, 6. This time I want the minimum. All right, and I'm just going to choose a place to the left. So, like let's say right there. So that vertical line is to the left of what I'm trying to find. Upper bound, just slide it to the right. Okay. So what's the minimum? -2.08. And it occurs at 1.15. Okay, so -2.08. It occurs at 1.15. Okay, and that's all you got to do. Okay, that's all we can do right now. Now, here's where I'm going to go ahead and take like a minute or so, and I'm going to go ahead and give you a preview of coming attractions. How many people in here are already familiar with what's called a derivative? Okay, you've already had some work in that. Okay, well, here's my question. This function, can anybody tell me what the derivative of that function is? Sir?
3x squared minus 4.
That's exactly right. Now, here's what happens. I'm going to show you at some point, probably 3-4 weeks, how to find the derivative of a function. But the derivative of a function is going to tell you the slope of a tangent line at some value of x. And that's very important to us. There's a lot of applications for derivatives. Okay. Now, what am I referring to when I say tangent line? How many points of intersection do I have? Only one. Okay. Well, this is very useful for helping me find these relative maximums and these relative minimums, because if I want this guy right here, that would be your tangent line. Well, what's the slope of that tangent line, do you think? What's the slope of a horizontal line? 0, okay? So if I want to know the value of x, okay, where that relative maximum occurs, I'm going to take the derivative and I'm going to set it equal to 0, because that's where I have a tangent line with a slope of 0. So check this out. Okay, what'd you say the derivative was? The derivative of this function is 3x squared minus 4. Don't worry about how we got that. Okay, I'll show you later. But I'm going to set that equation equal to 0. That's the slope of my tangent line, right? Well, let's go ahead and solve for x. 3x squared minus 4 is equal to 0. Okay, so 3x squared is equal to 4. Divide through by 3. X squared equals 4/3. How do I get rid of the square? Square root. And remember what happens when you take a square root. We were talking about that yesterday. The plus and minus. Let me show you this. So I'm going to come back over here. I'm going to take the square root, the square root of 4 over 3. Does that look familiar? Isn't that what we found when we were using the technology? Okay. So that is the point I want to be able to get to. But it's going to be a little while before we get there. Did anybody's Algebra 2 teacher, maybe if you had Heinrich, I don't know if he would have done it, f of x plus h minus f of x all over h? Does that look familiar to anybody? That's what we call the difference quotient. Okay, that is the universal way of finding a derivative. Okay, now what he did, more than likely, he just used the shortcuts. Satish, right?
Yes, sir.
Okay, he went ahead and used the shortcuts, which are much more useful, but until you recognize the patterns, you got to start with this. Okay, so if I lost you on the calculus portion with the derivative, fine. Just put it out of your head. Think of it as a bad dream. Okay, it's not going to come true for about 3 or 4 weeks. Okay, so we don't have to worry about it until then. All right. So as long as you can do or find the maxima and minima on technology calculator, you're going to be just fine. Okay, well, here's the last thing I want to go ahead and do. Okay, I want to go ahead and have just a quick review of even and odd functions. Okay, now we talked yesterday algebraically. Okay, is it Xavier?
Yeah.
Okay, up. Okay, here's what we were looking at. If I can take a function and I can replace x with his opposite, if I get the exact same function, does anybody remember what that was? Was that even or was that odd? That is even. Okay. So odd is if I can go ahead and replace x with negative x and get what? Negative f of x. If I get the opposite of what I started with. Now by opposite, I'm talking in terms of sign change. Positives become a negative and vice versa. Okay. So let's take a look at this guy right here. A. Is this one, is that already, is that implicit or explicit? Is it Zoe? That's not Zoe. Miriam.
Yeah.
Correct. Okay. Because Miriam and Zoe, they're very familiar. They're very like sounding. So I was close. Okay. I got it right. I'm still not 100%. I'm doing all right. Okay. Miriam, what would you say? Is this implicit or explicit? What form is it? It is explicit because it's been solved for what? It's y equals. It's solved for the dependent variable. Now, like one on B, what would that be?
Implicit.
That's implicit because it has not been solved for the dependent variable yet. Okay, so let's go ahead and try this. Let's plug in negative x and let's see what happens. So f of negative x equals 4 minus negative x squared. Now, I want to simplify as much as possible. But what happens when you square a negative? It goes positive, right? So this negative right here, he's got to stay the same. Nothing affects him. So take a look at what we ended up with. Did I get the exact same function? Is it the opposite or neither? Now, by opposite means the signs would change. So it would have to be negative 4 plus x squared. That's what I mean when I say opposite. So what happened here? It stayed exactly the same. So what does that mean? This guy's even. And if you go ahead and take a look, remember yesterday we said that even functions are symmetrical with what? Where could I fold and have the two parts come together?
The y-axis.
The y-axis. So we have symmetry with the y-axis. Now, the instructions say to go ahead and choose a point and show how it would be reflected with that. I'm not going to choose a specific point. Let's just choose a generic one. So let's say we take any point x, y on an even function. How is that point going to change if I reflect it with the y-axis? If I have that symmetry. Will the x change, the y change, or both? Just the x. Okay. And that makes sense because if I have this point right here, like let's say this point is, I don't know, 3, 2, and I'm just completely making that up, probably not on that function. This point over here, the reflection, that would still have to be negative 3, 2. Negative xy. Okay, so again, I just made that up. Odds are it's not going to be on that function, so don't, quote me on that. Okay, well, let's go ahead and take a look at C. Implicit or explicit? Implicit. Now, if you want to test for even or odd, you need it to be explicit. So let's go ahead and rewrite this guy. So the first thing I'm going to do is add x to both sides. Those cancel. 2y cubed is equal to x. What do I do now? Divide by 2. 2. 2. Those cancel. Y cubed is equal to x over 2. How do I get rid of a cube?
Cube root.
Cube root. That's the inverse. Okay. So my explicit function, y equals the cube root of x over 2. All right, now this is what I want to test. I want to replace every x with its opposite. So f of negative x, and we're not going to worry about doing b. It's on the notes if you want to take a look at it. But that's the cube root of negative x divided by 2. So x is just a number, right? It represents some location on your x-axis. So x divided by 2, that's just some numerical value. Okay? So here's my question. Can you take the cube root of a negative? Okay, yes. Remember, it only goes imaginary if it's in a square, like an even root. Square root, fourth root. So if I were to go ahead and give you, like, I don't know, the cube root of negative 8, what's that? Negative 2. If it's odd, then the answer is the same sign as your radicand. Okay, so it doesn't matter what x over 2 is, because it's negative, that means I'm going to get a negative answer, right? So how did these compare? Did they turn out to be exactly the same, or are they opposites? They're opposites. So what kind of function is this? It's odd. And you can definitely tell by looking at it what kind of symmetry is it going to have.
Origin.
Symmetry with respect to the origin. You remember yesterday I brought up a fan blade? Imagine if I just took this and I spun it 180 degrees, just half a revolution. I'm going to get the exact same graph. So this is symmetric with respect to the origin. Okay. And here's the last thing we're going to go ahead and do. Any point xy, what would it become after the reflection? Or, well, rotation, I should say. Would x change, would y change, or would both change? Both would change. Like you could have a point 1, 1, rotated around, it would become negative 1, negative 1. There you go. That's all there is to it. Questions? Okay. Well, you have your homework. Remember, that's due when? Not tomorrow. Okay, you can turn it in tomorrow if you want, but it's due Monday. So no rush on that. Okay, no rush. If you want to get it done before the weekend, completely up to you. Let's go ahead, clear your desks, please.